Welcome to the class. Dear students, today we are going to see what is hyperconjugation. But before looking at hyperconjugation, let us have a small revision on what is inductive effect. So what happens in inductive effect is the electron cloud is shifted towards the more electronegative atom. The electron cloud is shifted towards the more electronegative atom, and with the result a partial negative charge develops on the electronegative atom and a partial positive charge develops on the electropositive atom. So there is a polarization that is set up within the molecule due to difference in the electronegativity of the atoms. So therefore, inductive effect, another thing is that inductive effect is a permanent effect. That is, it will last as long as this molecule lasts, or it will last as long as this bond between these two atoms lasts. Only when this bond ceases to exist will the inductive effect cease to exist. So it is a permanent effect. So therefore, inductive effect is a permanent effect whereby polarization is induced in the molecule. And why is it so? Due to difference in the electronegativity of the atom. Therefore, what I have said, inductive effect is a permanent effect by which polarization is induced in the molecule due to difference in the electronegativity of the atom. Due to this difference, the electron cloud shifts towards the more electronegative atom, because of which polarization is actually induced. There are two types of inductive effects, minus I effect and plus I effect. This is the minus I effect. Okay, in the minus I effect, the electron cloud is shifted towards the substituent because the substituent is the more electronegative. In the plus I effect, electron cloud is shifted away from the substituent because the substituent is less electronegative or it is more electropositive. Okay, so plus I effect, in the plus I effect, electron pumping group may be attached. Therefore, electron pumping group may be attached or atom of lesser electronegativity may be attached. So therefore, the electron cloud is shifted away from it. So such groups display plus I effect. While in the minus I effect, the electron, this may be an electron withdrawing group, the substituent. It may be a atom of higher electronegativity, and because of which the electron cloud is shifted towards it. Now let us focus our attention on the plus I effect. We know the plus I effect, the substituent may be electron pumping group or it may be electropositive atom, because of which the electron cloud is shifted away from it, is directed away from it, and because of which it develops a partial positive charge. Which atoms, which groups display this effect, or which groups are electron pumping groups? There is no doubt in our mind that alkyl groups are the electron pumping groups. Alkyl groups are electron pumping groups. Now there are three types of alkyl groups. This is a tertiary alkyl group, secondary alkyl group, and these two are primary alkyl group. Shall we set it in the order of their plus I effect? If I set it in the order of their plus I effect, the most powerful plus I effect is produced by this. Why? Because there are three electron pumping groups. So the electron cloud will be shifted away from it, no doubt. Drastically it will be shifted. After this, rank will come to this. This is isopropyl group. There are two pumping groups here, correct? So the electron cloud will be shifted away from it, but not as like this. After this, this is the group, ethyl group. It is a primary alkyl group. Electron cloud will be shifted away from it, but not as much as this, because there is only one pumping group. And after this, finally you will get methyl. So the order of plus I effect is in this. This is the most powerful and this is the least powerful. There are three pumping groups here. So effectively the electron cloud will be pumped away from it. So this is the most powerful plus I effect that is being produced. Okay. Now hyperconjugation, let us come to hyperconjugation. This is not the case when R combines to carbon-carbon double bond. Okay, this order is not followed when R is combining to carbon-carbon double bond. When R combines to carbon-carbon double bond, plus I effect does not take place. When R combines to carbon-carbon double bond, plus I effect is not taking place. It does not exist. There is another mechanism of electron displacement, and that mechanism is called as hyperconjugation. That mechanism is called as hyperconjugation. In that hyperconjugation, you will see that the sequence is reversed. Okay, hyperconjugation, this will get number 1 rank, this will get number 2 rank, this will get number 3 rank, this will get number 4 rank. In plus I effect, this is the sequence. But when we say about hyperconjugation, this will be the sequence. Hyperconjugation is also shown by alkyl group. Plus I effect is also shown by alkyl group. The difference is hyperconjugation is shown when the alkyl group is attached to carbon-carbon double bond. And the another difference is that this sequence is reversed in hyperconjugation. Okay, so let us understand hyperconjugation by means of an example. Let us take propene, okay, and understand hyperconjugation. Propene, as you know, there is one double bond in propene and there is a carbon atom that is attached to the double bond, that can be said as the alpha carbon atom. So we will draw propene to better understand hyperconjugation. So this is your propene, right? This is propene. Okay, so let me draw the hyperconjugation for propene. Structure 1, structure 2, which I am drawing now on the board, and structure 3, which I am going to draw now. So there are 3 resonating structures. If you draw the overall resonance hybrid, it will look something like this. So that is propene, and we are seeing hyperconjugation in propene. You can see that alkyl group, which is the alkyl group here, the CH3 group. This is the alkyl group. How it acts when it is attached to carbon-carbon double bond? We are seeing the mechanism of electron displacement. In plus I effect, we have seen that electron cloud is directed. It is only the electron cloud which is directed towards the other atom. But in hyperconjugation, there is electron displacement. There is an electron pair displacement, not electron cloud displacement. There is actually a pair that is getting displaced. That is the difference between hyperconjugation and your inductive effect. In inductive effect, electron cloud is getting displaced, but in hyperconjugation, this pair, this sigma electron pair, this is getting displaced. So that is a main difference. And when it is occurring, when alkyl group is attached to this alkyl group, when it is attached to carbon-carbon double bond, when it is attached to carbon-carbon double bond, correct? Then hyperconjugation takes place. Now what happens in hyperconjugation? See, the CH bond here dissociates. When the CH bond here dissociates, the electron pair, it is left here. The CH bond breaks, H dissociates, it becomes H plus. This electron pair now comes as a negative charge over this carbon atom. Now this electron pair is directed towards the first doubly bonded carbon atom. This is the first doubly bonded carbon atom. It is directed towards the first doubly bonded carbon atom. Because it is directed to the first doubly bonded carbon atom, this double bond here, it becomes unstable and it appears as negative charge on the terminal carbon atom. Now this negative charge here, it is also unstable, correct? So it will come back here as double bond. When this comes here as double bond, this would become unstable and this would again become negative, correct? And this process will get repeated. When this is negative, of course this is unstable, it would come back here and the double bond would come back here and become negative charge on the terminal carbon atom. So this process is it becomes like a cycle. So this results in extension of molecular orbital and this results in delocalization over a large surface area. Delocalization of what? Delocalization of this electron pair. So this process results in a delocalization of the electron pair over a large surface area. If an electrophile would want to attack this pair, it won't be able to, because it would be very hard to find that electron pair, and that would make the propene molecule very, very unreactive and very stable. So it is because of hyperconjugation that the molecule of propene becomes very stable. It is because of hyperconjugation that there is delocalization of this electron pair over a large surface area. It is because of hyperconjugation that this molecule becomes very stable. So you can see that hyperconjugation is a kind of resonance. It is a resonance. Resonance because of breaking of the CH bond. Okay, the CH bond breaks and it assumes a no bond character. Okay, and because of assuming such no bond character, there is resonance, and therefore hyperconjugation is also called as no bond resonance. It is also called as no bond resonance. Hyperconjugation can also be called as sigma bond resonance. Why? Because a sigma bond has dissociated and it is interacting with the pi electron cloud, correct? So hyperconjugation involves the interaction of sigma electron of alpha carbon hydrogen bond with the pi electron of the double bond. Sigma electron of the alpha carbon, this is alpha carbon hydrogen bond with the pi electron of the double bond. And because it involves the interaction of sigma electrons of the carbon hydrogen bond with the pi electrons of carbon-carbon double bond, this is also called as sigma bond resonance. So these are the points. As you can see, propene, there are 3 alpha hydrogen atom. This is the alpha carbon atom. There are 3 alpha hydrogen atom. So there are 3 probabilities of hyperconjugation. So 3 resonating structures are formed, correct? For hyperconjugation to become operational, there should be alpha carbon atom and there should be alpha hydrogen atom. More the number of alpha hydrogen atom, more will be the hyperconjugation. Which is having more number of alpha hydrogen atom? Yes, methyl molecule, correct? CH3 molecule is having more number of alpha hydrogen atom. So which will show more hyperconjugation? Methyl molecule, correct? If a methyl group is attached, there are 3 resonating structures that can be formed. 3 resonating structures that can be formed. Suppose if ethyl group is attached. Suppose if, look at this. Suppose if ethyl group is attached, then how many alpha hydrogen atoms are there? 2. So how many structures will be formed? 2 resonating structures. So that would be less stable. So the hyperconjugation probability also will be less, correct? So methyl is greater than ethyl, correct? Now suppose there is this group, correct? There is isopropyl group. The probability of hyperconjugation again decreases because there is only one alpha hydrogen atom. There is only one alpha hydrogen atom. So the probability of hyperconjugation and the number of resonating structure also decreases. Therefore the stability of the resonance hybrid also will decrease. Okay. So again and again we are proving that more the number of alpha hydrogen atom, more will be the hyperconjugation. Now suppose if it is a tertiary butyl group, are there any alpha hydrogen atom? No. So hyperconjugation here will be 0. So the order of hyperconjugation, I have said initially that order will get reversed for alkyl group when we speak about hyperconjugation. So that order of hyperconjugation is, what is it? Methyl group shows the highest hyperconjugation, followed by ethyl group, followed by isopropyl group, followed by tertiary butyl group. Tertiary butyl group. So the hyperconjugation for alkyl group bonded to carbon-carbon double bond is in this order. For R group bonded to carbon-carbon double bond, hyperconjugation is shown maximum by methyl group, and then by ethyl group, isopropyl group, and lastly it is shown by tertiary butyl group. Tertiary butyl group hyperconjugation is 0. Okay, this is the minimum and this is the maximum. Correct? So this is the order of hyperconjugation. Now let us see hyperconjugation in determining the stability of carbocation. How hyperconjugation determines stability of carbocation? Let us see hyperconjugation and carbocation. So as we know, which is the most stable carbocation? Correct. You have guessed it right. This is the most stable carbocation, right? And that is followed by secondary carbocation, and that is followed by ethyl, and finally this thing. What makes this more stable? What makes this carbocation more stable? See, for carbocation to be stable, the positive charge here should reduce. It should decrease. The magnitude of positive charge here should decrease. There is an inductive effect that is in play in this carbocation. This inductive effect, there are 3 methyl groups, right? So they pump their electrons towards the positively charged carbon atom, and that would reduce the positive charge in this carbocation. That would make the tertiary carbocation more stable. Here there are only 2 groups. So what would happen? Only 2 groups pump their electron. There will be decrease in the positive charge, but not like this. Here there are 3 groups. Here there is only 1 group that can decrease the positive charge, and here there is no group. This we are speaking in terms of plus I effect. How can we relate this with hyperconjugation? See, for plus I effect we have said that there is, because of this plus I effect, tertiary carbocation is more stable than secondary, which is more stable than primary carbocation. What about hyperconjugation? How will we define, how will we argue for hyperconjugation? Yes, for hyperconjugation, look at the alpha carbon atom. How many alpha carbon atoms are there? Alpha to this positively charged carbon atom. Okay, you have to see alpha to this positively charged carbon atom. How many alpha carbon atoms are there here? 3 alpha carbon atoms are there. So how many alpha hydrogen atoms are there? 9 alpha hydrogen atoms. How many alpha hydrogen for secondary carbocation? 6 alpha hydrogen atom. How many alpha hydrogen for ethyl carbocation? 3 alpha hydrogen atom. How many alpha hydrogen atom? None. Right? So there are 9 alpha hydrogen atoms here. See, the 9, this is for 1. Okay, this is the case of 1. Right? So now what can happen? These are again I am not drawing full structure. These are again the methyl groups. This is for 1. There are 3 alpha hydrogen atom. Similarly here also there are 3. There are 3 here. What can happen? One of the alpha hydrogen atom can assume a no bond character. Okay, it can break a bond, and this pair of electron, it can come here, and an corresponding alkene can be formed. A corresponding alkene can be formed. So there are more chance of formation of alkene and more chance of getting rid of this positive charge in tertiary carbocation than for secondary carbocation than for primary carbocation. So in terms of hyperconjugation also, the tertiary carbocation is more stable than secondary than primary carbocation. So hyperconjugation also supports, also states, also argues, also defends the stability of tertiary carbocation. How it determines the stability? I have already said this is positive charge, and there are 3 alpha hydrogen atom, and it can, any of the alpha hydrogen atom can assume no bond character. Okay, and this pair of electron, it can come here and become an alkene. The main goal is to remove this positive charge. So in tertiary carbocation, it is more easier to remove this positive charge by the phenomena of hyperconjugation. So hyperconjugation supports the formation of a tertiary carbocation. Dear students, I hope you have understood. I hope you have liked the class. If you have done so, please do not forget to subscribe the channel, to like and share. Thank you very much.